second. Very good. There is some background noise, so please remember to mute your microphones unless you want to ask some question to our speaker today. So very good. So first of all, thank you everybody for being here. It's as usual an honor to have with us, in this case virtually, Sidney Redner, whom all of you know very well. Sidney Redner, he received his AB in physics from the University of California, Berkeley. Then he did his PhD in physics at MIT in 1977. Then he did a postdoctoral at University of Toronto, and after that he joined the faculty of Boston. He remained there for around 36 years, and after that I think that he moved to Santa Fe Institute, and he has been there for from that time. You will know Sidney very well. He has research interests broadly in statistical physics on non-equilibrium and applications to a variety of phenomena. He has an outstanding list of articles with very influential ones. Overall, he has around more than 250 articles, and he has two very well-known books. One that we know very well, A Guide to First Passage Processes, and another one of a kinetic view of statistical physics. So Sidney, thank you very much for being with us today in Mexico City virtually. Welcome to the Universidad Autónoma Metropolitana. And please go ahead, we are all yours.
Okay, well, thank you very much for a kind introduction, and it's nice to participate with you again. I mean, unfortunately, it's virtual, and I hope that sometime soon it can be in real life. So I want to discuss with you some very recent work I've been doing in a very pleasant collaboration with Benjamin de Bruyne and Julien Randon-Furling, and it's applying first passage ideas to problems of optimization and wealth sharing. So let me begin at the beginning, and I'll start by just defining what is a first passage process. Many of you probably are familiar with it, but just I'd like to start at square zero. And then I want to introduce to you the notion of first passage resetting. So this is a variant on the classic resetting problem in which the resetting is induced by first passage process rather than just happening at a random rate. And then I'll turn to two applications. One is using first passage resetting to control an optimization problem. And the second one is dynamics of wealth sharing. And you'll see how resetting emerges as kind of an underlying theme in both of these two applications. So first of all, what is a first passage process? So imagine that you have a child who is now grown up and leaves the house, and your child wanders around the world. And let's suppose that the world is a one-dimensional world. And so your child wanders around looking for opportunities here, there, and everywhere. And a question you might be interested in asking is that, will you see your child ever again? And if you do see your child, how long do you have to wait before your child returns, under the assumption that your child is just doing a random walk in one-dimensional space of opportunities? So these are the two basic questions that underlie first passage processes. Will the walker ever return to the starting point? And if the child does return, what is the first return time? How long do you have to wait before you're going to see your child again? So these two questions basically underlie a first passage process. And so let's answer for this basic first passage process, because it can be done very simply using very simple ideas. So let's talk about, or let's calculate the first passage probability in one dimension. So the first passage probability is the probability that a random walker first reaches a given point x at time t. So if we are imagining that here is the x positive, this is where your child is wandering around. And if your child happened to start at x naught, we know that in the absence of any kind of other boundary condition, this would just be a Gaussian spread around x naught. But there's a new twist to the problem, because if we reach the origin, that means that we're done. We've returned home. And effectively, that means that the probability is removed from the problem if it ever reaches zero. So we have to deal with a boundary condition at the origin that there's no concentration at the origin. And the simplest way to enforce this is by using the image method of electrostatics, that is, include a anti-Gaussian centered at minus x naught, and by symmetry, the concentration at the origin is necessarily going to be zero. So this is basically the solution to the problem with the boundary conditions. So for x positive, the superposition of the Gaussian and the anti-Gaussian gives you the full probability distribution in the region x greater than 0. And so so to compute the concentration in the region x greater than 0, we take the original Gaussian and add to it with a minus sign, the anti-Gaussian, which is centered at minus x naught. So this is the full probability distribution in the region x greater than 0. And once we have the probability distribution, then we can easily calculate the flux, the diffusive flux to the origin. And that diffusive flux is what is basically the first passage probability, because of the boundary condition that if you hit the origin, you're removed from the system. So whatever flux hits the origin coincides with the first passage probability. So this diffusive flux, which is nothing more than the gradient of the concentration, this defines the first passage probability. And here the x naught refers to the starting point and t is the time. So this is the first passage probability to the origin. And from this concentration profile, we compute the first derivative, we set x equals 0, since that's what we're looking for, and we get a very simple form for the first passage probability. And this innocuous form has two amazing features associated with it. The first one is that if we now compute the integral over all time of this diffusive flux, or this first passage probability, we get amazingly 1. So it means that no matter it means that all the probability is eventually absorbed at the origin. So you are guaranteed, if you send off your child in a one-dimensional universe, that your child will eventually return home. On the other hand, notice that for a long time, the exponential factor goes away, because for a large time this becomes 1, and we have a t to the minus 3/2 tail. And if I compute the first moment, or the average time of a distribution with the t to the minus 3/2 tail, you get infinite. So one has this very strange dichotomy that you're sure to return, but you have to wait an infinite amount of time before you return. And this dichotomy between, sure eventual return and infinite return time is what makes one-dimensional diffusion still a very subtle process, and a process still actively studied after more than 150 years. Okay. So with that little preamble, let me now go to resetting processes. And the pioneering paper in the subject was Evans and Majumdar. And what they did was simplicity itself. And it's just a really good lesson that sometimes simple things work really well. And their basic idea was, let's study diffusion, but let's imagine that every once in a while, we just put our random walker back to the origin. So here is kind of a space-time picture of it. So in constant rate resetting, or Poisson rate resetting, here's a space-time picture of the trajectory of a random walk. So x is vertical direction, time is going to the right. And so we just, every once in a while, we reset back to the origin. And then we go again and reset back to the origin. Go again and reset back to the origin. Go again and reset back to the origin. And so this is all there is to it, to the resetting process. And the crucial element in this is that there is a resetting rate that you, the user, can choose. And so the time between resetting events is 1 over the reset rate. So this is the classic resetting process. And now let me turn to first passage resetting. So this problem was first considered in a very different context by Falco and Evans in 2017. And what I'm going to present to you now is the work of Benjamin and Julian, in the past year. And so in first passage resetting, we reset a random walk not at a given rate, but when it first reaches a given threshold level. So in first passage resetting, we say that when the random walker reaches a fixed threshold L, which we are free to choose, then we reset back to the origin. And again, we wait until we reach L again and reset back to the origin, and we continue on. And every time we reach L, we are reset back to the origin. So in our problem, the reset rate is determined by the first passage time. And the crucial difference between these two processes is that in constant rate resetting, this reset time is a finite number. whereas in our problem, the reset time is an infinite number on average. And this difference between finite and infinite means that this is actually a stationary process, whereas this is a non-stationary process, and that has fundamental ramifications. So I want to present two aspects about first passage resetting. The first question you might want to ask is, what is the probability distribution of a diffusing particle that's moving by pure diffusion plus first passage resetting? And then I'll turn to a very simple optimization problem that naturally emerges from this first passage resetting problem. So if we want to compute the probability distribution, there are two ways to do it. There's the easy way and there's the hard way. And the hard way is basically you apply renewal theory, and one can write like a nice renewal equation for the evolution of the probability distribution, because every time you reset to the origin, the problem restarts again. And even though it's a pleasant calculation to do, it's not something that I want to present in a seminar. So I'm going to present the easy way, is by doing it by a geometric path decomposition. So let's look at how we can use path decomposition to understand the role of resetting on the trajectory of a random walk. So here I'm showing you now a trajectory of a random walk where I have a third passage to a distance L away. So after the first passage, I'm reset to the origin. The second passage, I'm reset to the origin. And then there's finally a third passage. So the third passage probability to x equals L with resetting, notice that there's a very simple equivalence, because if I just shift these two segments, I shift the green segment by L and I shift the blue segment by 2L, what we get is a first passage path to 3L with no resetting. And so there is a very simple geometric equivalence between first passage to L with resetting and nth passage to NL without resetting. So again, there's no sleight of hand here. It's just shifting my trajectories in a very simple way. And I can use that simple trick to actually compute the probability distribution of the particle for x positive. So let's do that. Let's now compute the probability distribution for a particle when x is bigger than 0. And notice, because I'm setting my reset distance at L, I can't be beyond L, because if I hit L, I'm always reset back to 0. So my final position is somewhere between 0 and L. So here is an example of a trajectory that has 3 resets, and then it's somewhere between 0 and L. And we want to compute this probability distribution. So we want to compute the probability that being at x between 0 and L, in this case with 3 resets, but in general, it could be any number of resets. And again, using this path decomposition trick, we see that by shifting this thing by 1L, this by 2L, this by 3L, that the final position lies between 3L and 4L. It can't be anywhere else. And so the probability distribution of being at x equals L over here is the same as the probability of an unrestricted diffusion being at x equals 3x plus 3L. That's how much you've shifted by. And moreover, the maximum of the random walk has to be less than 4L, because if it hit 4L, then that would be another reset. So there's a simple geometric equivalence between the position distribution of the particle with resetting and the position distribution of the particle with no resetting. And now this is the thing that we want to compute, the probability that we're at a position x equals, that we've been shifted by 3L upward. And so here's the initial position. And the maximum had to be less than 4L in my particular example. And fortunately, this quantity is well known, because Levy, the Paul Levy of fame in random processes, computed the probability that for a diffusing particle to be at position x at time t with a maximum, and my mouse stopped working, 1 second. Anyways, with a maximum m, which is obviously larger than x. So we're going to make use of Levy's formula to actually compute the probability distribution. So here's the part involving this geometric path decomposition, which is the probability of being at position x at time t with x positive. Well, first of all, there can be any number of resets. And for a given number of resets, we just do that shifting of the trajectory of our random walk. And we have our particle at position x plus nl with a maximum larger than less than n plus 1l. And then this probability is exactly Levy's formula. We just plug it in here. And the only new feature is we have to integrate the maximum from the position of the walker up to like the maximum position it could be without another additional reset. And so we have the formula. This is an elementary integral, and you do it, and you get some nice looking formula for the probability distribution, which also you can compute by this path decomposition approach. So that was for X positive. For X negative, it's even cooler what you can do, because, as I'll try and illustrate here. So let's look at a random walk or a diffusing particle that starts at the origin, has undergone 3 resets, and the final position is at X, which is less than 0. And here is a simple way that we can compute the probability distribution for a diffusing particle which has an odd number of resets. And the idea here is you take the segment before each odd number resetting, and you just translate it upward by L. So I'm doing just, rigid translation, and then I flip. And you see now that the trajectory starts at L and ends at X. And this is pure diffusion with no restrictions of any kind. So this just gives us pure diffusion from L to X. On the other hand, if I have an even number of resets, then I take the green segments before each even numbered resetting, I shift it by L, translate it by L, just like this, and then I flip those segments, and you see that I have, again, pure diffusion with no restrictions that starts at the origin and ends at X, where X is less than 0. So that's what we get. And so the probability distribution when X is negative is just the sum of these two contributions, just this. So it's really quite remarkable that, like, the summation of all these different resettings, if you do it in the right way, you end up with a very simple formula. And in fact, if you do this by the renewal equation approach, again, you have an infinite series, but then magically it factors, and you end up with just these two terms. So this is basically solves the problem of first passage resetting. What is the probability distribution of a random walk? And in distinction to the case of constant rate resetting, in which case there is a steady state probability distribution, here the probability distribution continues to evolve with time, so there is no steady state. Okay, so now let me turn to the first application of first passage resetting, and that is to, like, an optimization problem. And again, I'm a theoretical physicist. I know nothing about real machines. I don't touch them. I don't, for me, a screwdriver is an implement of mass destruction. So here is my attempt at modeling some kind of a mechanical system. I have an operating coordinate, X. And if I'm thinking about a car, I can think of X as like the RPM, the rotations per minute, revolutions per minute of the engine. And so this is the basic coordinate that tells us how hard the mechanical system is being driven. And the idea here is that if we have some kind of a mechanical system, we'd like to drive it hard. We don't want to drive our car at 5 miles an hour. We'd like to drive it at 50 miles an hour. And so we'd like to be somehow close to the right-hand side of this operating coordinate. But on the other hand, if we are too close to, like, high RPM, and most cars that have a tachometer will have a red line, and if you go beyond the red line, that's dangerous because the engine could break down. And so if you break down, what you have to do is you have to go by the side of the road and call the tow truck and have the car sent back to the shop, in which case they repair it, and then you restart and you start over again. And so this is our kind of naive picture of, like, how any mechanical system ought to operate. There is some range over which the mechanical system should operate. You'd like to operate it close to maximum performance, but if you go too far, the system breaks down and you have to take it to the repair shop and start over again. And we want to try and use first passage resetting to just mathematize this picture and actually figure out what is the optimum performance of such a system. So we need to have some kind of a metric that allows us to quantify the performance of the system. So clearly you want X, the operating coordinate, to be close to L. And on the other hand, we want to minimize the number of breakdowns. So here is a natural way of defining an objective function that kind of incorporates the balance between these two attributes. So we integrate over, we have like a long period of time over which we're running our machine. So we integrate over this operating time, x of t divided by L. So when x is close to L, this quantity is large, and we'll get a large positive contribution if we operate near L. But also there's breakdowns. And so every time there's a breakdown, so n of t is the number of breakdowns in a time interval t, and c is the cost per breakdown. And if we're running this in a steady state for a long period of time, if we divide by 1 over time, this is going to go to a steady state quantity, which is proportional to the length of time that the system is operating. So we divide by 1 over time to get a time independent quantity. And so this is the objective function that we want to try and optimize. And so that's the goal of the story. And again, the crucial point is that there is breakdown whenever we reach L. And so this is a first passage resetting problem, because when X reaches L, then we reset back to the origin and start over again. So now, in order to solve this problem, we have to, whoops, now something just happened here. Okay. My keys have somehow shifted. Anyways, this is the thing that we want to optimize. And we need one more feature to this, which is we have to decide how we're going to operate the system. And so what we did was like the most simple-minded thing to do, which is what I call the floor-it protocol. And the floor-it protocol is what happens when you're 16 years old and you get the keys to your daddy's car for the very first time, and you're at a stoplight, and your daddy has a big, huge Oldsmobile with a V8 engine, and the light turns green, and you put the pedal to the metal, and you put a big patch of rubber on the ground. So this is what I would call the floor-it protocol, which is whenever you have the car, you put the pedal to the metal all the time until the car breaks down, and that's what we do. The thing is that this is actually very naive, and one person has now written paper with much smarter protocols. But the nice thing about the floor-it protocol is that it's sufficiently simple that we can understand everything in complete detail. So this is a very busy slide, and don't take it too seriously, but I just want to give you a sense of like how we solve the problem, because it involves just standard technology, and it turns out to everything kind of worked very nicely. So the thing is that in this floor-it protocol, that means that we're pushing the system towards breakdown. So that means that we want to solve the convection diffusion equation. Here, the subscripts denote partial differentiation. And so we're solving the convection diffusion equation with a source term at the origin, which is the flux that leaves the right edge. So if the car breaks down, and the rate at which you break down is the diffusive flux to the right edge, you're re-injected back at the origin. So we want to solve the convection diffusion equation subject to, we start at the origin with the absorbing boundary condition at x equals L, and the initially empty system. And we're solving this in the steady state, and so it's a linear equation. It can be solved. It's very standard technology, and you end up with a steady state concentration profile. Then the second thing that we need is a number of breakdowns, because that's the second part of this of the objective function. And so we need to compute the number of breakdowns. We first have to compute the first passage probability to the right edge of the interval. So here is the first passage probability. And here it turns out to be convenient to write everything in the Laplace domain. So the tilde above and S means the Laplace variable. So we're computing the flux to the right edge of the system. And again, this is a one-dimensional geometry. We're solving a linear equation. So to compute this flux is easy. It's not necessarily easy, but it's standard technology. And so one gets some nice algebraic expressions for the first passage probability. And then the only other thing one needs is how we compute the number of breakdowns. And to do this, we use renewal theory to say that if we have a breakdown at a time, if we look at the number of breakdowns up to time t, well, if I had n of t breakdowns at time t prime, then if there's a first passage and the remaining time left, that adds 1 to the number of breakdowns. So there's a very simple renewal equation for how the number of breakdowns evolves with time. And again, in the Laplace domain, this convolution becomes an algebraic equation, one can write a simple algebraic equation for the Laplace transform of the number of breakdowns, and then you get the number of breakdowns in the real-time domain. And it looks a little bit messy, but again, standard technology. And so once we have these two components, the steady state concentration profile from which we can compute the steady state value of the position and the number of breakdowns, we can then compute this objective function. And so here is the final result of this objective function as the function of the Peclet number, which is how hard I'm stomping on the accelerator on my car. So positive Peclet number means that I'm trying to drive the system towards breakdown. Negative Peclet number means I'm driving it away from breakdown. And here we see the behavior of this objective function as a function of the cost per breakdown. And it turns out here to be convenient to define the cost per breakdown normalized by the diffusion time, just because we get simple numbers. And if the cost per breakdown is very small, well, then it means that if you break the car down, it takes 5 minutes to go to the shop and fix it and have it as good as new, then you might as well like push the car to the edge all the time. And so you see that there is an optimum of the objective function for positive Peclet number, which means you're always driving the system to breakdown all the time. So if breakdowns are cheap, you should drive it towards breakdown. On the other hand, if the cost per breakdown is large, this red curve, that's kind of like the F-35 fighter in the US Air Force, which is like, each copy is $400 million. And it takes, I think like for every hour it's in the air, there's 20 hours of time in the shop. So basically you only drive like your F-35 fighter or your Ferrari sports car, you only drive it like once a week or once a month because it's so expensive to run it. And so when the breakdowns are expensive, you drive it away from breakdown and you see the optimum value of the Peclet number is negative. So you're basically driving it away from the breakdown point. So this shows you how this combination of first passage resetting and, in this very toy model of a mechanical system gives you a very nice and non-trivial optimization problem. So that's sort of like the first half of my talk. And what I'd like to do now is tell you some work which is not yet published and we're still grappling with it. But I want to describe to you wealth sharing by first passage resetting. And the inspiration from this work comes from a very beautiful paper by two very well-known probability theorists, Henry McKean and Frank Shepp in 2006. So let me first tell you what their problem is, and then I'll tell you what we've done. So in their problem, they're trying to understand the role of wealth distribution on economic activity. And so they thought about the simplest model they could possibly think of, which is just two people. So your society consists of two people, and they're diffusing on a one-dimensional line, and their position on the one-dimensional line is how much money they have. So in the absence of any other attributes going on, their wealth just diffuses, and if they reach the origin, that means they've gone bankrupt. But now there's one more aspect to this model, which is that there is God above. So God is looking down from above, and she has perfect knowledge of the position of these two people. So she knows how much money each of these two agents has. And God has one unit of velocity that she is free to distribute to either of these two agents as she sees fit. So she might want to give 1 unit of velocity to the poorer person, or 1 unit of velocity to the richer person, or maybe she gives the same amount to each of them. And the question is, what should God do to optimize the system? And here comes an interesting problem, which is, what do we mean by optimize? And it turns out that depending on your criterion for optimization, there's different strategies that are actually better. And in the paper, they describe what they called the Robin Hood strategy, which is always giving to the poor, or the George Bush strategy, which was always giving to the richer. And it turns out, depending on what you want to optimize, it's either the Robin Hood or the George Bush strategy is actually better. So I'm kind of leaving this a little bit vague and not very well answered, because I'll leave it to you to maybe look up their paper. But the thing about this model was that what makes it difficult is that the two agents are actually moving by diffusion plus convection, because when God gives you some unit of bias, then we have, each of the agents is moving by convection plus diffusion. And convection plus diffusion is much harder than pure diffusion. So what we were trying to think of is, could we come up with a model in which is only pure diffusion and also self-contained, no external agents, and have a non-trivial optimization problem? And so this is the problem that we came up with, which was egoism versus altruism. So here is a space-time representation of the amount of money that an egoist has as a function of time. And now let's suppose we have, and again, in the spirit of simplicity, let's just have two egoists. So if we have two egoists, well, they move by diffusion, and eventually we know that one egoist goes bankrupt, and then the other egoist goes bankrupt. So there's no doubt they both will go bankrupt. And the thing that you might want to ask is how long do you have to wait for the first guy to go bankrupt, how long for the second guy to go bankrupt, and how much money they might have on their way to bankruptcy. And so the model that we've looked at was one in which we have altruism. So we have the same two agents, but instead of when one agent goes bankrupt, the other guy doesn't care one way or the other and doesn't even look. Here we say that whenever somebody goes bankrupt, the two altruists have made a pact. If I go bankrupt, I ask the other person for half of his wealth or half of her wealth, and we've agreed in advance that whenever someone goes bankrupt, we equally share the remaining wealth, and then we can start over again because now we're no longer both bankrupt. So in the altruist scenario, the initial up to time T1, everything is exactly the same, but after time T1, we're going to start halfway in between and continue on until the next bankruptcy. And in the first case, the blue guy went bankrupt. Now the red guy went bankrupt. And again, we share our wealth equally. And then there's another bankruptcy, et cetera, et cetera. And so the question we want to ask is, which strategy is better? And so again, we have some questions about how to compare, like which strategy is actually better. And there's different criteria that we might want to think about. And I'm going to answer some of these questions. And as you'll see, that maybe they answer the question of which strategy is better and maybe they don't. So first question is like, when does each egoist go bankrupt? When do altruists go bankrupt? What's the dynamical behavior of the wealth of the system? So we can answer some of these questions. And so like I want to present in the next few minutes, just some of these answers, because they're kind of, they're fun things to think about. So first of all, we need, let's go back to something much simpler, which is just the wealth evolution of a single agent. Because when I first solved the problem of first passage, where I showed that if you start with a diffusing particle at position x naught, so now x naught is representing how much money they have, we know that he's going to go bankrupt for sure. But we also know that the time to go bankrupt is infinite. So like, how can we characterize the behavior of the money of this agent? And it turns out that the average wealth is a very bad characterization because the average wealth is fixed. And the mathematical reason for that is that this is a martingale process, what mathematicians call a martingale. And also you can just do it by direct calculation of computing the average position of the walk. But I mean, the crucial point here is that in pure diffusion, at each step, you either move equal distance away from the origin or towards the origin. So at every single step, your mean position doesn't change. And if you've hit the origin, then by definition, your mean position doesn't change. So for all possible trajectories, the mean position doesn't change. And so the average wealth is fixed. So average wealth doesn't really tell us anything about this time evolving trajectory, which hits the origin. And so what we've looked at is the typical wealth. And so, oftentimes the word typical kind of means wishy-washy, like, sort of average something. It's not very well defined. But here I want to give a well-defined meaning to typical wealth by saying that if we integrate the probability distribution of the random walker, over all x, then the typical wealth is defined by saying that half the probability distribution is between the typical wealth and infinity. And similarly, the remaining half of the wealth is between 0 and x typical. So this now gives a more precise meaning for the term typical wealth. So let's ask ourselves, how does the typical wealth of a single agent evolve? So the thing is that we know what the probability distribution is because it's this, it's the Gaussian plus the anti-Gaussian. So what we need to do is we have to take this probability distribution of the random walk, and we want to integrate from xt to infinity. And so this involves just the error function complement. And then and we want to solve for xt, the typical position x. So this is a transcendental equation that you can't solve analytically, but you can certainly solve it numerically. And if you do that, you get a very nice plot and so I'm plotting now the typical wealth compared to the initial wealth and plotted versus time. And here the natural unit of time is the diffusion time. And one sees that this typical wealth just has a very nice smooth behavior and reaches zero around 1.1 times the diffusion time. So this gives a more precise meaning for the notion of typical. And one other thing I just wanted to add to this, which is that if you think about a nearest neighbor random walk in one dimension that starts at distance 1 away from the origin, it turns out that after 10 steps, 90% of the probability has already been absorbed. And so the typical event is that you get absorbed in a time which is of the order of the diffusion time. So let's now use the same picture to understand the behavior of two egoists that ignore each other. And so what we need to do is, like in the same way as before, we need to compute the probability distribution. So first of all, we have to compute the probability distribution of each egoist, and then do the spatial integral and set it equal to 1/2. So let's look at, first of all, the first egoist to go bankrupt. And so here is the position distribution of the first egoist. And in this particular case, we have to normalize it by the probability that he has survived. So this is error function of the probability that a diffusing particle has not hit the origin at time t. And then this prefactor is a probability that both people are still alive at time t. So this error function cancels one of the error functions of the denominator. And again, when we do the integral, these involve error function complements, and you get a very simple looking equation for the behavior of the typical value of the position as a function of time, which again, you can't solve analytically, but one can solve numerically. And similarly, for the second egoist, it's the same thing as before. We want to compute the position, so here is the, Gaussian plus anti-Gaussian probability distribution of the walker. We have to divide by the probability that the walker, we have to normalize it, but that's again the error function. And then we would have, and this prefactor in front is the probability that there's at least one walker still alive up to time t. And so again, it's it's a bunch of little algebra, and you get a transcendental equation that you have to solve. And at the end of the day, this is what comes out of this. So for the first egoist to go bankrupt, he goes bankrupt at basically half of diffusion time, and his wealth just plummets right away. The second egoist is taking advantage of the fact that he's the one who's living longer, and he dies, or he loses all his money after 3.5 diffusion times, but it's a non-monotonic evolution of the wealth as a function of time. And this could be generalized for any number of agents if you'd like. So now that we've understood the wealth evolution of two egoists, now let's look at the wealth evolution of two altruists. And this turns out to be considerably more subtle. So first thing is to compute the wealth distribution at the first individual bankruptcy event. So imagine that you start with each agent with wealth 1 or wealth x naught, it doesn't matter. And we just ask, when one guy goes bankrupt, how much money does the other guy have? And so again, what we need to do is we have to compute the first passage probability to bankruptcy for one guy. And we want to integrate over all possible times that this first bankruptcy can occur. So here is again the sum of so this factor is the Gaussian plus anti-Gaussian, this is for the guy who's alive. And this x naught over e to the minus x naught squared over 4 dt and 4 pi dt squared. So sorry, I'm jumping a little bit ahead of myself. This thing with 1 over square root of 4 pi dt is just the probability distribution of the spatial distribution of the guy who's alive. And then there'll be an x naught over 4 pi dt cubed square root e to the minus x naught squared over 4 dt. That's the first passage probability. And the 2 accounts for the fact that either guy could be the first guy to go bankrupt. And so this tells me what is the position distribution of the guy who's alive when first passage occurs. And I just have to integrate this thing over all time. And very beautifully, this has a very simple form. And notice that the position distribution has a 1 over x cubed tail. So it's got a long tail associated with it. So this now tells us how the wealth evolution changes every single time there's an individual bankruptcy event. So here I started x naught, but I could start at x sub n minus 1 and I get the new value of x. And so this, sort of Cauchy-like distribution is the distribution of wealth after, if you start with the wealth x n minus 1, you ask at the next bankruptcy, how much money do I have? And the amusing feature about this wealth distribution is twofold. One is that the mean wealth is fixed. That is, if I compute xn average, it's the same as xn minus 1. So the average wealth is fixed. But more interestingly and more relevant for real life simulation is that the most probable value of x is going down systematically at each event. So here's what we find. The average wealth is fixed, but the most probable wealth at the nth step is the most probable wealth at the previous step divided by square root of 2. So what you see in the simulations then is that all of these realizations, they go bankrupt pretty quickly because the most probable wealth is going down by a factor of 1 over root 2. There are very few and rare realizations where the wealth is increasing, but they're become more and more rare as time goes on. So now we need to like finish the story. We have to decide like how do we define how the two altruists are actually bankrupt, because we see that there's like the first bankruptcy event, the second bankruptcy event, the third bankruptcy event, and the total amount of money is sort of systematically going down. And so we need some sort of cutoff criterion to define like when both people are bankrupt. And arbitrarily, we just said when you reach 10 to the minus 4 x naught. So if you started, say, with $10,000 and you reach $1, well, once you have $1, you can't do anything. You can't even go to a grocery store and buy a candy bar because they're all more than $1. So we define like if you have $1 in your pocket or 10 to the minus 4 of your initial wealth in your pocket, that's basically you're bankrupt. And so if the typical or the most probable value of the money is going down by a factor of root 2, and you want to reach 10 to the minus 4, that corresponds to 27 individual events until both people are bankrupted. So let's look now at the dynamics of these bankruptcy events of these two altruists. So I'm plotting here simulation data, and here on the left, I'm plotting the probability of bankruptcy at the nth event. And so, nth event means n individual bankruptcies where one guy goes bankrupt, they share the money, they start all over again. And you see that our prediction of 27 bankruptcies, it matches pretty well with the peak in the distribution itself. On the right, I'm showing the probability of bankruptcy, again, joint bankruptcy at time t. And this has a heavy tail. This is plotted just on a linear scale, but there's a long tail here. And once again, we can make some sort of criterion for like, what is the typical time it takes for the two people to go bankrupt? The average time is certainly going to diverge, but the typical time, which would be saying that the integral under the curve, set it equal to 1/2, that will define a typical time. And so if we do that, we find that half of the probability is less than 2.21 diffusion times. So a typical bankruptcy time is 2.21 diffusion times. And now we have beginnings of an answer to like which strategy is better, because we can compare the bankruptcies of egoists versus altruists. So the first egoist went bankrupt at half a diffusion time. Two altruists go bankrupt at 2.2 diffusion times. And the second egoist goes bankrupt at 3.45 diffusion times. So if you're going to ask like which strategy is better, well, clearly, if you're the second egoist, you say, well, I'll be an egoist, and if I see my partner go bankrupt, I just ignore him. But the problem is that if you say at the beginning you're the egoist, Well, it could be that you go bankrupt first, and then the other guy, your partner, is laughing at you. So it's sort of like playing Russian roulette with a chamber that has, you know, two chambers with one bullet, and, you know, if you pull the trigger and you blow your head off, well, tough luck. If you don't, if the other person blows their head off, well, then you're feeling pretty good about yourself. But the problem here is that if you have only one life to live, you see that the average of the lifetimes of the two egoists is less than the lifetime of the altruists. So depending on, like, if you want to be risky and say, or if you want to just look at the average behavior, it tells you that the criterion for deciding which strategy is better is actually is somewhat up in the air. All right. Another thing that you might want to look at is the wealth of the egoists versus altruists. And so here again is the plot I showed before of the wealth of the first egoist, the wealth of the second egoist. And numerically, this is what comes out by from the wealth of the two altruists. So altruism means that you're going to do better than the first egoist, but you're not going to do as well as the second egoist. And if you want to try and be a little bit more circumspect and look at the average of the first and second, well, I'll come to that in just a moment. So the last thing that I want to present on a technical side is just like, what is the dynamics of the bankruptcy of altruists? And this is where we come to like the really challenging part of the problem, for which we don't really have, for which we have like a pretty good answer, but we're still grappling with it. And the reason why this problem is tricky is the fact that we're trying to compute the nth passage probability, where n is roughly 27, because when we hit 27 bankruptcies, that means we're both bankrupt on average. We want to compute the nth passage probability, but the point is that every passage has a new starting point. So the initial condition for the nth passage is determined by the position after the n minus first passage probability. So this iterative aspect to this first passage problem is what makes this problem both interesting and challenging at the same time. And let me just show you what the best data that we have for this, which is, I'm showing now the time integral of the first passage probability from t to 3/2 t. So basically I'm doing a logarithmic binning and I'm computing the integral of the first passage probability. And you see that we have a large range of times over which we have a behavior that kind of looks almost power law-like, because it looks like a straight line on a double log plot. And so, what we can say at this stage is that it looks like a power law, but we have strong reasons to believe that there's logarithmic corrections in this expression. So we believe that asymptotically, it's something like log t over t squared is the asymptotic behavior of this of the first passage probability, which would correspond to a log t over t for this integrated quantity. So this is actually something we're grappling with right now, and I think it's kind of an open question. Anyway, so which strategy is better? Well, one thing I didn't talk about, but I mean, I can give you a concrete answer, is what if your criterion is to maximize the probability that you're both still alive. Well, then clearly altruism is better, because if in the case of the altruists, in the case of the egoists, when the first guy goes bankrupt, the second guy goes bankrupt, and that's the end of the process. But in altruism, when the first guy goes bankrupt, you're actually helping him a little bit by sharing. And it turns out that it's easy to show that both the agents are, that there's a higher chance that both agents are viable when you have altruism. Another natural criterion might be maximizing the survival probability. And again, the question is, what do you mean by maximizing the survival probability? Do you want to maximize the survival probability of one, the other, the average? And so here is actually simulation results of the survival probability versus time. And again, you see that it's better to be the second egoist compared to the first egoist, because altruist is somewhere in between. But on the other hand, if you want to say, well, the most prudent thing is to say, let me compute the average survival probability of the egoist, the average is less than that of the altruist. So if you're the second egoist, you should say you should be an egoist, but if you want to be more prudent about it, then it seems that altruism is better than egoism, because altruism is better than the average of the green and the blue curves. So for maximizing the survival probability, I would say the answer is it depends. And the other thing you might say is, well, let's maximize the wealth. And again, the answer is it depends on what you're talking about, because here, again, I'm showing the same plot as before, but I'm not computing the average of the two egoists. And you see there's a range of time in which altruism is better than the average egoist, but most of the time the egoist average is better than altruist. But certainly the second egoist is better than the altruist over the entire time range. So again, it depends on what you mean by maximizing the wealth. Do you want to do it for each person or for the average ensemble of people? So I'm basically at the end of the story here. And I hope I've given you a sense that first passage resetting is a new type of stochastic process. It's a natural extension of good old Poissonian resetting, in which the reset is determined not by just an external user that has some random clock to decide when to reset, but it's determined by the first passage problem itself, first reaching a given threshold level. And so there's many interesting aspects about of this first passage resetting that I think are fun to think about. And even the issue of just the probability distribution of the diffusing particle with first passage resetting was highly non-trivial. And so what we did find was the probability distribution by a nice path decomposition approach. And as I mentioned, one can also do the same kind of calculation by standard application of renewal theory. I then turned to looking at optimization in a toy model of a mechanical system. And clearly, this is highly deficient, because we really need to have a more realistic picture of what a mechanical system is, and moreover, how to have control protocols which are more realistic. I mean, clearly, when you're pushing your car to the red line, you would ease up on the accelerator. And we did not have that feature in our kind of modeling, but that's sort of a natural thing that might want to think about. And then finally, I talked about the dynamics of wealth sharing, and we came up with a very simple model in which we were trying to compare egoistic behavior versus altruistic behavior. And we have partial answers for like the dynamics of the wealth in both the egoistic and the altruistic societies, but we don't have like a really crisp answer at this stage of like which strategy is better, because it depends on the nature of what criterion you want to use. And finally, the other aspect about this problem, which I think is really challenging and fun, and there's a lot more we can say about this, is that this is an interesting iterative first passage problem in which we're looking at the nth passage probability, where the nth passage probability depends on what happened at the n minus first passage probability. And finally, one other thing I should have said, I didn't put it here on the slide, is that all of these questions can also be naturally generalized to any number of agents, and we have some partial answers for any number of agents as well. Okay, I am done. Thank you for your attention. I hope everyone's still there.
Thank you very much, Sidney. I think it was a fantastic talk. I personally always love the way you managed to put a story behind all this very nice and derivations you do. We have time for questions. Colleagues, please, if you have some questions, just directly unmute your microphone, or maybe raise the hand, or just activate your screen and say hello so I can see you. Questions?
Well, I have one question.
Okay.
Please go ahead, Annie.
Hi, Sidney.
Hi.
Yeah, regarding the first problem of first passage resetting and this analogy with free diffusion problem, have you considered the case where X is always a positive quantity? For instance, that you have a reflecting boundary at the origin. Could you, in principle, use apply this idea, right? And to optimize similarly as you do?
Well, so I guess what I'd say is if I put in a reflecting boundary at the origin, then this problem will end up going to a steady state rather than being like
Yes.
continually evolving. So I would say that with the reflecting boundary condition, although it might be mathematically a bit more complicated because you have to deal with another boundary condition, somehow it strikes me as a simpler problem overall just because it goes to a steady state. So I think it might be very sort of like in a similar universality class to the original Evans-Majumdar problem.
Okay, and precisely with the Evans-Majumdar problem, can it be solved using this path translation technique that you introduced? Maybe it could be, because I haven't seen it among the many methods that they've used.
Yeah, no, that's a funny thing you mention it because yeah, it seems like that should work even for their problem as well. I mean, the thing is that their problem is so simple in the end because you just end up with an exponential probability distribution and you're solving a simple steady state equation.
Yeah.
But no, I hadn't thought about that possibility of using that same technique in this case. So yeah, interesting to think about.
Okay, thank you.
Sure.
Thank you, Danny, and thank you, Sid. Any other questions?
Nice. Carlos Pineda has his hand up.
Ah, yes. Sorry. Sorry, Carlos, go ahead, please. Thank you.
So I have a simple question. What happens with another strategy in which, let's say, one of these two persons simply gives all the wealth to the other person at the very beginning, so he goes bankrupt.
Okay.
And the other first person then would have like more time to. I guess that would be a better strategy, no?
No, it's not actually. I mean, because I mean
a little bit.
Pardon me?
No, if you could.
The thing is that, like, at the moment of bankruptcy, if suppose that one agent has a wealth W and the other is 0, so then they both go to W over 2. So, like, what you're saying is, if I have two agents at W over 2, and then I say one agent gives all his money, and so the other agent has wealth W now. So that's exactly like the time reversed of like of the redistribution that we do in this sort of socialistic model. And it's a very strange thing that we cannot find like a really crisp answer to like which strategy is better, because it depends on whether you're talking about the wealth, the survival probability, so it's not obvious which one strategy is better than the other.
Okay, thank you, Carlos and Sid, for the answer. Any other questions? Very good. So if not,
Yeah, maybe I had an additional question. Sorry.
Please, of course, Danny,
sure.
Go ahead. Yes.
So the numbers that you've presented in the altruist problem, how do they depend on this threshold, epsilon or 10 to the minus 4?
The threshold, like 10 to the minus 4. I mean, the point is that, excuse me, because like you're getting closer and closer exponentially. If you change the threshold 10 to the minus 5 or 10 to the minus 6, that makes an exponentially small correction to the actual numbers themselves. So as long as the threshold was small, it doesn't matter really what it is.
Okay.
Thank you. Any other questions, colleagues? Okay. I remember that I don't see you. If you're saying no with your head, I can't see you. Okay. So so very well. So Sidney, it was a pleasure to have you back again.
Sure.
Virtually Mexico City. I hope that when all this nightmare passes, we can you can visit us again. Okay.
I'd be glad to.
You're always welcome here. So let us thank the speaker, please, again, with maybe virtual applauses. Thank you very much, Sidney.
Sure.
Excellent, guys. So see you in 1 week. Remember that in 1 week, I think we have Jorge Castañeda. And in a couple of weeks, remember that we are going to have the 2 Nobel laureates speaking here in this seminar series. We'll have Bill Phillips and Tony Leggett. Okay, so I'll keep you posted on the various seminars. Thank you very much, and see you next week. Bye bye all.
Okay.
Bye-bye.
And Sidney,
Goodbye, Sid.
So I'm staying, right?
yes, Sid. So,
Okay.
bye.
Bye-bye.
Gracias.
Bye, thank you.
Hasta
So
luego.
long.
Nos vemos, Denis.
Hasta
Nos
luego.
vemos. Chao.
Bye.